We've talked about position, velocity, and acceleration, and now that we've looked at vectors, we can look at these three guys in 2 and 3 dimensions. So let's go ahead and draw a three-dimensional position vector. First, I'm going to lay out a coordinate system. So there we go, we got x, y, and z in this direction. And incidentally, these three have always got to be in that orientation relative to each other. So we could sort of rotate it. We could do, maybe x could go this way, and then maybe y is going back sort of into the page. And if we do that, then z has actually got to come down and be like this. So they're in the same relative orientation. We'll talk later about how, kind of why that is and how you figure out what the correct orientation is, but for now, just know that that's a thing. All right, so I'm going to draw my position vector r, and I'll draw it like that, and I'm going to put a little parentheses t in there to remind myself that r is a function, and a little arrow over it to remind myself that r is a vector. And then I'm going to pretend I'm shining a light down from z, and I am going to show you the shadow of my r vector in the x and y plane. And then I can draw a little line out here, and a line this way, and I'm doing this, I can erase that now, so you can see that I've got an x component, a piece of r that's in the x direction, and a piece of r that's in the y direction. So let's go ahead and draw those guys out. We'll do x in blue. So that is the piece of my vector r, which is in the x direction. I'm going to draw that as x sub t. So this is my x position. It's t because it's a function, and also it's different from this x. This is the vector, sorry, this is the axis x. This is the x component of the r vector. We've got a y component as well. I'll draw it like this in purple. And that's y sub t, the y piece of the r vector. And then we can extend our little box lines. We'll go straight up here and over like this, extending the shadow into the x and z plane. And there's our box that makes up r. R starts at the origin here and goes out to this corner of the box. And now we can draw our z vector. I'll do that in orange. There's the z vector, that is the z piece of r. And now I can write out r in component form. So it would be the vector r, which is a function of t, and that's equal to the x piece, and that's in the x direction, so we need an I hat, plus the y piece. That can change with t, and it's also in the y direction, so we need a j hat, and the z piece. Again, still a function of t, might change with t, and it needs a k hat because it's in the k direction. And now we've got the position vector all drawn out. We can treat it like we treat any other vector. So we can do addition and subtraction. If, for example, we are looking at displacement, change in position, we would subtract the position vector at a later time, we'll call it t2, from the position vector at an earlier time, we'd call it t1. And to write that all out in components, we'd look at the x pieces. So we'd subtract x at t2 minus the x position at t1. Maybe I'll do square brackets since we already got parentheses. And that, of course, would be only in the x direction. We'd have the y component. So the y piece of the position at the later time t2 minus the y piece of the position at that earlier time t1, and that would be in the y direction. And then we'd also have z. So the z piece of the position at that earlier time minus the z piece at the later time minus the earlier time, and all of that in the z direction. So that's how you do displacement, same as you would for any vector. Subtract the two vectors means you subtract each of the components one by one, keeping them carefully separated using their unit vectors. You can also do derivatives. So if you want to know the velocity in 3 dimensions, you take the derivative of the position with respect to time. And that will flip out into the derivative of the x part of the position in the x direction, using an I hat vector to denote that. The derivative of the y part of the position, that's of course in the y direction, and the derivative of the z part in the z direction. And this is actually 3 different equations, because of course this v, we could rewrite that as the x piece of velocity, which is in the x direction, the y piece of velocity, which is in the y direction, and the z, and the z piece of velocity, which is in the z direction. And that's equal to all of this. Derivative of x in the x direction, derivative of y in the y direction, and the derivative of z in the z direction. And so when I say this is actually 3 different equations, what I mean is things in the x direction can only influence the other things in the x direction. So anytime you see this I hat, you can actually pull everything that's next to the I hat out into its own equation. So let's go ahead and write that. So this guy could become 3 independent equations. We'll have the x equation, which will be the x component of the velocity is equal to the derivative of the x piece of the position. You'll have a second equation about the y piece of the velocity, the y component. And then, of course, a third one about the z component of the velocity. And mathematically, these 2 ways of writing it are exactly the same thing. This is just saying we're using the hat vectors to separate out the 3 bits of information, and here we've just written into 3 separate equations. Both exactly the same. And of course, you can do the exact same thing with acceleration. So if we want to write acceleration compactly, we can write a is equal to the change in the velocity with respect to time, the derivative of velocity with respect to time, or we can sub in what we know about velocity and say we're taking the derivative of velocity, but velocity itself is the derivative of position. We can make that a little more compact by using this notation, where we do d squared of the position r over dt squared, and that just means take the derivative twice, like this. So we can write it compactly like this, or we can split it up into 3 equations like we did here. We can say the x component of the acceleration is equal to the derivative of the x component of velocity, or the second derivative of the x position. And then we can write a second equation, which is just the y, looking at the change in the y piece of the velocity, or the second derivative, change in the y component of the position, and then a third equation for z, change in the z component of the velocity, or second derivative of the z component of the position. And one of the really great things about vectors is the dimensions are truly independent of each other. So what's going on with z, you only have to deal with it in the z equations. What's going on in y, again, that only is going to influence what's happening in the y chunk of the equation. And same with x. So you can look at the acceleration in x separately, and then later on switch over to y and do all of your y stuff, and then later on switch over to z. Or alternatively, you can solve all 3 of these equations and then combine the information separately. Or sorry, combine the information together. Let's see what that looks like in terms of constant acceleration. So when you've got acceleration, you can split this up into the x piece of the acceleration and the y piece of the acceleration and the z piece of the acceleration. And of course, in general, these guys are going to change with time. That is, they're going to be functions of time. And if that happens, then we have to go and do integrals of the acceleration to find the velocity, and then integrals of the velocity to find the position. But if they aren't just any old functions of time, but they are constant, and it doesn't have to be all three of them, it can be just one of them. If, for example, ax is constant, then you can use all of the constant acceleration equations only applied in x. So, for example, the x position is equal to the initial x position plus the initial x component of velocity times time plus 1/2 the x component of the acceleration times time squared. You can get the x component of the velocity is equal to the initial x component of the velocity plus the x component of the acceleration times time. You can get the x component of the velocity squared is equal to the initial x component of the velocity plus 2 times the x component of the acceleration times the difference in the x position, and so forth and so on. I guess what else? We can do the difference in the x position is equal to 1/2 the x velocity plus the initial component of the x velocity times time. Remember this guy, that when acceleration is constant, the 1/2 plus the 2, the sum of the two velocities, that's the average velocity. Only true when acceleration is constant. And then totally separately, you can treat whatever's going on with ay. Maybe ay is constant, maybe it isn't. Maybe ay is 0, but it is completely separate from what's going on in x. And so if you need to, you can integrate this. You can make up its own set of constant accelerations. So say it is constant. Then you can say that y is equal to the initial y position plus the initial y component of the velocity times time plus 1/2 the y component of the acceleration times time squared. You can do the y component of the velocity is equal to the initial y component of the velocity plus the y component of the acceleration times time, and so forth and so on. One thing I do want to point out is I haven't put a subscript on time, and that's because time doesn't get divvied up among x, y, and z. Time is shared between all the dimensions, because of course if you think about it, what we're doing is we're splitting up where we are, in the x direction. Maybe that's east and west. In the y direction, maybe that's north and south. And so you can walk in just east or west, and north and south. But when you're looking at the whole picture, when you figure out, what's my final time, well, all of your coordinates have to arrive at the final location at the same time. So time doesn't get split up like the position vector does, or the velocity vector does, or the acceleration vector does. And that's because time isn't really a vector. So time is shared in between all three directions. But the position components and the velocity components and the acceleration components are each unique to their own direction. It's only when you want to combine all the information back together and being very careful to say, all right, here's the x information, but remember that's only in the x direction. That's why I got an I hat here. Here's all the y information, but that's only in the y direction. So I got a j hat here, so don't mix these two up. And then here's your z stuff, but it's only in the z direction. So again, don't mix it up here. Only when you combine it like this and you get the full vector, that's when you finally pack all of your information together. But until then, you can solve it each separately in its own equation.